Okay, so I'm going to go ahead and solve the fence problem from exam 3. I suggest that in a moment from now when I tell you, go ahead and pause, read the question, just so it's fresh in your mind, and then hit play before you listen to this video. Okay, go ahead and pause now. Okay, now that you've reread the question, the first thing that we're asked is what are the dimensions of the field that can be enclosed for the least cost? So least cost is our main focus. We'll worry about how much the fence cost and after that. So our objective function is least cost. The cost that comes from paying for all the fence, which we'll find by multiplying the dollar amount times the perimeter, including all the walls, not just the outer perimeter. So there were 4 outer walls, the 2 X's and the 2 Y's. And there were 2 inner walls we have to pay for, the x/3 length wall and the y/4 wall. So now we can multiply these with their cost. The 4 outer walls cost $8 each, and the 2 inner walls cost $12 each. Simplifying this algebra, just multiplying really at this point and canceling my fractions, I've got all the costs, but to clean up my objective function, I should combine like terms. So now I have one objective function. So now that we have the objective function, we're ready to find the constraint function. As you read the question, hopefully it caught your eye, that it says the total area needs to be 6,080 square feet. So area equaling 6080 is our constraint, and area is found by multiplying the X and Y, the outer walls together, that come together in a 90-degree angle. Now we need to solve this constraint for one variable so that we can plug it into the objective function. Taking xy equals 680 and solving for x, so I divide both sides by y, I'll get x equals 6080 over y, and I can plug this into my cost function where x was, multiplying and rewriting the y variable with a negative exponent from the denominator. I've got my cost function, and I'm ready to minimize this function. So now we need to take the first derivative of the cost function to find critical values, because that's the only way we'll get the x or y values to minimize cost. Copying the cost function from before, I'm now ready to take the first derivative, which needs to be set equal to 0. And for me, to solve this, I'm going to go ahead and add the opposite of the first term to both sides. Cross multiplying is the next method I'm using, but you can choose to use whatever method works for you. And to continue solving for y, I need to divide both sides by 19. And now I can take the square root of both sides. Technically, you take plus or minus the square root of the left to get plus or minus 80, but we know length cannot be negative. So the only critical value we have is y equals 80. Now we want to use the second derivative test so that we can prove that 80 was a minimum. So I've copied the first derivative over, taking the second derivative. So now I need to test the critical number in that second derivative. My critical number of 80 gets plugged in, and using my calculator, I've got 0.475. Because this number is positive, it's in a concave up region, and so my critical number would be a minimum. Now let's find x. If you remember before, we had the equation x equals 60 over 80y, where I'm just going to swap my y out with 80. This is when we solve the area function for x. And I get 76 for x. And lastly, I need to find the cost. Going back to the cost function, plugging in my x of 76 and my y of 80, I get 3,040. Lastly, we can answer the question. X equals 76 feet, Y equals 80 feet, and the total cost was $3,040. So my units on dimensions were just feet, and my units on the cost was dollars.